The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone, and thank you for joining. My name is Amy Rose. I'm an engineer in the Strategic Energy Analysis Center at the National Renewable Energy Lab. And thank you for joining our latest in the India Modeling Spotlight webinar series, where we highlight NREL's publicly available tools for use in power sector analysis in India. Today, we're focusing on the Probabilistic Resource Adequacy Suite, or PRAS tool. PRAS allows users to identify areas of highest risk in their system and quantify system reliability. It also allows users to estimate the contribution of new resources, such as wind and solar, to resource adequacy, a topic that is increasingly important in India as the share of renewables continues to grow. Our presenter today is Sarah Awara. Sarah is an electrical engineer at NREL. She specializes in resource adequacy with a focus on evaluating the capacity credit of renewable resources. Before I hand it over to Sarah, just a few notes. First, this webinar is being recorded, and we will make the recording available after the webinar. And second, if you have any questions at any time, please go ahead and enter them in the chat window. We'll collect all the questions as they come in and answer as many as we can. Thank you, and with that, I will hand it over to Sarah.
Thank you, Amy. All right, so as Amy mentioned, I'm an electrical engineer in the Grid Systems group at NREL, and I'm really excited to be talking about PRAS today, which is one of NREL's resource adequacy tools as part of the India webinar series. All right, so PRAS is a resource adequacy tool, and it can also compute capacity credit. And today I would like to start off by reviewing and defining some of the terms that we use a lot when using PRAS to make sure that we're all on the same page. And then I will dive into what PRAS is and what are some of the features of PRAS, and then go over some examples where PRAS was used. All right, so NERC defines resource adequacy as the ability of the supply side and demand side resources to meet electrical demand. So through resource adequacy assessments, we're trying to answer the question, is there enough power available in the right place at the right time for my system to serve loads with acceptably low shortfall risk? And the term acceptably low shortfall risk is very subjective, so I'll talk a little bit more about that in some later slides. All right, so the motivation of most resource adequacy assessments is that we're trying to figure out where and when does the shortfall occur. And this is a small demonstration here that shows where the shortfall is happening and the amount of shortfall and when is it happening through the time that you could see here. All right, so system operators have been using the planning reserve margin for resource adequacy assessments for a while, where they consider the system to be resource adequate if the installed capacity exceeds the expected peak load by a certain amount. So for example, here you could say, I consider my system to be resource adequate if the installed capacity exceeds my peak load by 15%. Historically, this was very easy to calculate, and our systems were mostly contained a lot of dispatchable generators as opposed to systems today, which contain relatively higher penetration of variable generation. Therefore, it's hard to determine what the reserve margin should be, since with the planning reserve method, you can't really account for uncertainties such as peak load forecast or variable generation. Therefore, over the past few decades, researchers have been very interested in the probabilistic resource adequacy assessment, which provides a more rigorous quantification of the shortfall risk using more detailed probabilistic metrics. And the most commonly used metrics are the loss of load expectation, EUE, and UEE. So the loss of load expectation is a probabilistic expectation of the number of hours with shortfall during an analysis period, and the units for this specific metric is usually expressed in hours per year. So usually the analysis period is over a year. For the expected unserved energy, we're looking at the probabilistic expectation of unserved energy during an analysis period, and the units for that is usually megawatt hour per year. And then you have the normalized EUE, which is basically a fraction of the demand unserved during the analysis period. So it's the ratio of the EUE to the total demand. So as I mentioned at the beginning, that the term low shortfall is very subjective. And since no system is 100% reliable, we kind of use these metrics to express how adequate our system is. So mostly in North America, a system is considered to be resource adequate or reliable if the loss of load expectation is less than 2.4 hours per year. Okay, so as Amy mentioned, India is planning to install 450 gigawatt of renewables, mostly wind and solar, by 2030. And this introduces a lot of generation uncertainty to the system due to the variability of these resources. Therefore, capacity credit is a good metric to measure the contribution of a resource in terms of firm capacity or conventional unit. So really what we're trying to figure out through capacity credit is how much can each generator contribute to meet the system's firm capacity at a specific point in time. So for example, if we're looking at a 100 megawatt wind farm, how much of that 100 megawatt can we actually rely on to meet some shortfall in the future? So with conventional power plants, it's easier to determine the capacity credit due to you don't have any of the variability variability of generation similar to wind and solar resources. So it's easier to say that the capacity credit is proportional to the installed capacity. And with conventional units, you're only taking into consideration forced outage rates when you're calculating its capacity credit. On the other hand, for wind and solar, you can't really say that the capacity credit is proportional to the installed capacity because you have to take into consideration forced outage rates and also the variability in the generation for these resources. Although capacity credit is a good metric to determine the contribution of these resources, however, it gives you no specific information on expected frequency, duration, and magnitude of capacity shortfall. And it also does not consider the impact of transmission congestion and outages. However, it's still a good option to look into the contribution of non-conventional units. All right, so there are two main classes for calculating capacity credit for the methods. So we're looking at approximated based methods, and these are usually mostly used by system operators. And then you have the probabilistic based methods, and these are usually used by academia. However, a lot of system operators are starting to use those methods or are looking into those methods. And I'll go a little bit into more detail over the next coming slides. So with the capacity credit approximation based methods, and these are mostly based on capacity factor approximations. So there are various methods out there. The two most commonly used methods use the net load, where they examine the output during periods of the highest net demand. And the other method is using the loss of load probability and examining the output during the periods of those highest LOLP. Those methods are simple and they've worked with specific systems. However, there are some downsides to it. They're often very sensitive to the chosen periods of the highest net demand, whether you decide that you're taking the top 1% of the hours or the top hours or the top 100, you might be getting different values. And then with some systems, the highest net load hours may not be the highest risk. We've seen other systems where you might see your highest risk during periods where you have high maintenance for your generators. So that's also another downside. And with this method, you're not taking into consideration transmission. However, with probabilistic-based methods, you're using the reliability metrics that I mentioned, the LOLE, the EUE, and the NAUE. And with those systems, with the probabilistic methods, you're taking more things into consideration. And when I start talking about PRAS, I'll kind of go over that. However, I just want to give you a high level of how two of the commonly used methods. Here I'm looking at the ELCC method. So the way to compute the capacity credit using this method is, first of all, you look at your system where you don't have your added new generation, which is basically the curve here in blue. And then you add your new generation, whether it's a wind farm or a solar farm, or whatever unit. This method is applicable to conventional and non-conventional units. So now your reliability curve shifts a little bit to the right, and your system becomes, if you want to say, more reliable. So what you're trying to do is you're trying to achieve the same reliability target after you add your new generation unit. So basically, the amount of added load that you could add to the system is your capacity credit. So in this specific example, we can say that the capacity credit is 400 megawatt for this added new unit. With the EFC method, here you're trying to express your added unit in terms of firm capacity. So basically, if you have your 100 megawatt wind farm, and that 100 megawatt wind farm can reduce your EUE or LOLE, depending on which unit you're using. Here, I use EUE. So say it reduces your EUE by 100 gigawatt hours, and you have a 45 megawatt firm capacity that provides the same 100 gigawatt hour reduction, then you can say that that 100 megawatt wind farm is equivalent to a 45 megawatt firm capacity, or you could simply say it has a capacity credit of 45%. Okay, so here I have some examples of system operators and how they calculate their capacity credit. So we talked about the two main methods for calculating capacity credit, which is the approximation-based and the probabilistic. But when system operators don't have enough operational data, they sometimes assign a fixed capacity credit to the unit. So MISO for new solar units, they assign a capacity credit of 50%. However, when they do have some operational data, so for solar units and PJM for solar and wind, they basically compute the average capacity credit of the resource during the 3 most recent summer periods, which is usually from June to August at hour ending 3 p.m. To hour ending 6 p.m. However, MISO uses, for wind, they actually use the probabilistic-based method. However, they don't have enough operational data right now for solar. So that's why they're either going with the fixed capacity credit or they're going with the average capacity factor for solar. So for the probabilistic-based method, so as I mentioned, MISO uses the ELCC method for calculating capacity credit of wind. And PJM is also looking into that. PJM is concerned about the penetration of variable resources increase and the potential of reliability impact on of the peak load shift on the system, and that would not be captured by the capacity factor method. So they're also looking into the ELCC method for for both solar and wind. CAISO, on the other hand, they use the ELCC method to calculate the monthly capacity credit of wind and solar. All right, so now that we've talked a little bit about what resource adequacy is and capacity credit, we can dive into what PRAS is. So PRAS, as Amy mentioned, stands for the Probabilistic Resource Adequacy Suite, and that's NREL's collection of tools for studying unserved energy risk in electric systems across both space and time. And the two main functions of PRAS is that it quantifies the shortfall risk using the standard probabilistic metrics, such as loss of load probability, loss of load expectation, expected unserved energy, and normalized expected unserved energy. And it also determines resource adequacy-based capacity credit metrics such as equivalent firm capacity and equivalent load carrying capability of individual resources, which is the two methods that I explained a few slides ago. And PRAS is open source and it's available, so you could download it from GitHub and start using it. All right, so I kind of want to go through over an example or the problem formulation of PRAS. So for example, consider that you have a system of 5 different regions. Here we named them A to E, and each region has VG profiles, dispatchable units with their forced outage rates and load, and they're all connected through transmission lines. So PRAS would consider your variable generation profiles, your load profiles, the dispatchable generator availability, so the outage rates, the dispatchable generator capacity, and also the transmission availability, so the outage rates and the transmission constraints. However, it does not take into consideration costs and prices, and it does not perform unit commitment or economic dispatch. And that allows for significantly faster solves and for you to explore possible operating conditions through the Monte Carlo simulation. And typically, with a lot of our studies, we're typically looking at 1,000 to 100,000 annual simulations for generator outages, load, and VG. All right, so with PRAS, you could basically pick whatever you want depending on what you want your results to look like. So for example, say you have your system import, so your import data could be from Plexos or from other planning models, and then you get to tell PRAS how you want it to model your VG, and then also you get to pick which simulation method you want to go with. So whether you want to go with a non-sequential copper plate or a non-sequential network flow. So non-sequential means that your time periods are independent of each other, as opposed to sequential, which is mostly used when you have storage on your system, where your time periods are dependent on one another. With a copper plate, that's when you're looking at all your regions individually. However, with network flow, that's when you're taking into consideration transmission between regions. Then you can express your results in terms of spatial or temporal, or both spatial temporal. And then you can pick the adequacy metric that you would prefer, whether it's LOLE, UE, or NUE. And then if you also want to take it a step further and calculate capacity credit, you also have the option of picking that. Yeah, so for example, you could say, okay, so I want to input my data from Plexos. I want to consider, so backcasting is when you consider your VG and load to be fixed with no uncertainty. And then you could say, okay, so I want to go with a non-sequential network flow, I want to express my results in spatiotemporal and express them in terms of EUE, and then calculate my capacity credit of the unit in terms of equivalent firm capacity. Yeah, so here, kind of summarizing again what I just mentioned. So with backcasting, you're taking your VG and load data as fixed. And then the non-sequential, you're assuming that your shortfall risk in each hour is evaluated separately and independent of the risk in other hours. And there's no link between the timestamps. And then with the network flow, you're considering your VG load and dispatchable in the individual generators or in the individual regions, but you're also taking into consideration the transmission between those regions. Okay, so PRAS is open source, as I mentioned. And it's free and available, and you could download and start using it whenever you wish. However, you might need Julia on your computer, and the memory requirements really depend on the number of samples that you're running. However, ideally, based on experience, we've seen that 8 or 16 gigabytes would be better. Okay, so here, this is an example of a project that was done at NREL, where the results from PRAS were expressed in terms of spatiotemporal, and they were expressed in terms of NUE. So the nice thing about this simulation, or about the results that you could get, is that you could figure out where and when is your shortfall. So if I could replay. Okay, well, it kind of keeps coming. So for example, here you could
Hi, everyone. It looks like we may have lost Sarah for a minute. We'll try to get her connected again. We did have a couple of questions come in through the chat, and we'll have time to go through those at the end. So please, if while we're waiting, if you have any questions, feel free to add those in the chat box, and we'll collect all of them.
Hi, Isabel.
All right, it looks like we have Sarah.
Yeah, I'm sorry, I got kicked out. Pretty odd. Sorry about that.
No worries.
Right, so
Let me know if you have any trouble resharing your screen.
sure. My presentation is taking a while to open here. I think I got kicked out of the VPN. All right. Can you see my screen right now?
Yep, we see it and it's in presenter mode.
Okay, I apologize about that.
No worries.
All right. As I was talking about the simulation right here, so here you could see the spatiotemporal shortfall for North America. So as you can see, like the summers are usually where you see a high of shortfall risk. The fall is not as much. However, as the winter progresses, as the day progresses during the winter, you also see a lot of shortfall in the northern of North America. So this is one of the applications of PRAS. The other is calculating capacity credits. Here with this project, we were looking at the 20 kilometer, we were looking at the resolution of adding wind to a 20 kilometer by 20 kilometer grid cell across the Western US. And the nice thing about this plot right here is that you could see where your capacity credit is highest. So for example, for offshore wind right here, we see that mostly you get your highest capacity credit right here. So if as a developer, you can decide that this is where you want to build your new wind to get your maximum capacity credit, and hence that would meet your shortfall. For this specific plot right here, we use the equivalent firm capacity method to calculate the capacity credit. Okay, so what types of questions can be addressed with PRAS? So PRAS really quantifies the shortfall in a power system using the reliability-based metrics that we talked about, taking both into consideration generator and transmission outages. And it also determines the capacity credit of the generator in terms of those metrics. However, PRAS cannot do detailed unit commitment, merit order dispatch. So the kind of questions that you could answer with PRAS is when and where are the shortfalls in a power system? And what is the capacity credit of wind or solar or even a conventional unit? But most of the time we're interested in renewable generators in a specific region. Okay, so to conclude this presentation, so wind and solar can contribute to meet the firm capacity obligations. We just need to use methods to calculate the capacity credit so that we can take into consideration the uncertainty, the variability, and see how well the wind and solar profiles correlate with the demand. Although a lot of approximation-based methods are being used by system operators, however, probabilistic methods are becoming more popular because they could take into consideration more aspects, such as transmission. And also there is a lot of research going on the best methods to model transmission and to also look at the impact of different regions on each other. So I'd be happy to answer any of your questions at this time.
Great, thank you very much, Sarah. We do have a couple of questions, and for those who are joining, feel free to keep adding questions in the chat as we go. We'll have some time to get to all of them, I think. So first, a question on kind of capacity credit methods for hydro. You talked about wind and solar,
Okay.
but hydro is
Yeah.
a bit tricky because you have to think about, seasonal and interannual variations in hydro availability. So
Right.
can you comment about how PRAS treats hydro, specifically storage hydro?
Yeah. So so PRAS treats hydro as a conventional unit, or just like VG, where you have like your forced outage and it looks at the profile of hydro. I'm not aware of any specific considerations for hydro as opposed to other units. So
those inputs would be like historic generation to get a hydro profile?
Yes. Yeah.
Okay.
Yeah.
Okay. And then for other types of storage, how is capacity contribution for energy storage considered?
Okay. Yeah. So energy storage is unique in the sense that PRAS actually dispatches storage in a method that is called realization dispatch. So it actually goes and it sees where the shortfall is occurring, and then it would dispatch your storage unit, as opposed to a lot of methods in the literature that maybe look at the loss of load expectation over the entire analysis period, and then determining where the dispatch is occurring. However, with PRAS, it actually looks like as it's calculating the LOLE or EUE for every time period, if there's a shortfall at a specific time period, it actually dispatches. So it's not based on any economic, so it doesn't do any energy arbitrage, similar to a lot of what's out there in the literature. It looks only at the shortfall.
Okay, that's helpful. And then another capacity credit question. So for renewables, as you increase the geographic footprint of wind and solar, the capacity credit could increase. It sounds like PRAS calculates capacity credit for specific projects or specific sites, but is there a way to look at more of kind of a multi-site, like renewable fleet? Or maybe that's not the right term, but
okay, so you mean like multiple wind farms at the same time?
And understanding kind of how the complementary sites might increase the overall capacity credit for all of the wind farms in a particular area.
Yeah, so basically with a capacity credit calculation, you're comparing your original system, which could have solar or wind, with another system where you're adding the unit that you want to calculate the capacity credit of your added unit. So you're comparing between these two systems. So your second system where you're adding your new generator, yes, you could add like 100 units and then calculate the capacity credit of that collective 100 units. Did I understand your question correctly?
Mm-hmm. Yeah, that's helpful.
Yeah, so it doesn't have to be a specific unit. It could be a bunch of units. Yes.
Okay. Then a couple questions about inputs, and then we'll go to questions about outputs. But
Sure.
first on some of the model inputs. PRAS is taking in results that could come from a production cost model or a planning model.
Yes.
But what specifically are those? Are those snapshots in time of system conditions of here's the load and here's how different generators were dispatched to meet that load and line flows?
Yeah, so basically what PRAS does is it grabs the conventional units and the VG, and if you have any forced outage rates that you've assigned in your Plexus model, it also grabs those. It grabs your load profiles, the VG profiles. However, for storage, as I mentioned, even if your Plexus model dispatches storage in a different way, PRAS would grab the storage data, but it would still dispatch it in its own way. So your Plexus dispatch of storage will not necessarily be transferred to PRAS. And that's sometimes an issue that we do encounter, is that if we're grabbing load profiles from Plexus, where those load profiles already take into consideration the storage dispatch, and then you might actually not get like an original load profile in PRAS. So that's something that you have to kind of be aware of. So what we actually do sometimes is we get PRAS to read the load specifically from CSVs, so that we can get the original load profile for the demand versus one that takes into consideration maybe the charging and discharging of the storage units.
Okay. And then is this for 1 year, or can you use multiple years of load and variable generation profiles?
You could do it for multiple years.
Okay. And then, so aside from kind of known things like forced outage, can you also use PRAS for more extreme events with low probabilities? And has that been done at NREL?
I believe you could, and I think it has been used. It wasn't on a project that I was working on, but I think Josh worked on a project that did that. Yeah.
Okay.
Josh,
So
Novacek. Yeah. Yeah.
So then a question about some of the outputs and what users can do with the outputs. So you showed the nice map of the US that showed high risk areas at different times and how that changes at different times of the year. But when you actually get the outputs out of PRAS, what level of detail are you getting? Can you see, for example, what's contributing to shortfalls, whether it's a transmission outage or generation, so that users can make some kind of actionable plans to reduce these outage probabilities?
Yeah, I think with the older version of PRAS, that wasn't a feature. However, Sinead Murphy has been working on code where you can actually output some of that data.
So you can see, okay, we have a big risk and in New England at this time of year, and that's due to transmission congestion. So the solution would be
so basically you could output the transmission, but it wouldn't like, there isn't a specific feature in PRAS where it's telling you this shortfall is caused by this specifically, but you could definitely output a few things and then look at the data and come up with that conclusion.
Okay. Yeah. Sure. I'm sure it's rarely just one cause, right? It's all the different systems.
Yeah, because sometimes it could be multiple things.
Okay. Well, that brings up a good point, which is PRAS in a is it continuing to evolve? Are you all continuing to make changes and updates to it? Or is it
Yes.
kind of finished as is? Okay.
Yes.
So what kinds of updates could we expect?
So for example, with the newer version of PRAS that we're testing right now, you could actually model solar and storage coupled systems, and that wasn't a feature in the older version of PRAS. Also, in the older version of PRAS, we couldn't actually take into consideration forced outage rates of variable generation or variable generators, and now with the newer version, we can. So yeah, so as we're going along, Gord Steven is doing a great job at adding new features to PRAS to make it more flexible.
Okay, great. So something to look for. And then a little bit outside of PRAS, but more in terms of applications and what's actually being done in practice. So you showed some examples of what's happening in different RTOs in the US. Do you see an overall shift in system operators moving towards probabilistic-based methods?
Yes, for sure. Yeah. Yeah. So especially that as you're increasing, so the thing is with capacity factor methods, it doesn't always capture the effective high penetrations of renewables on the capacity credit. However, with the probabilistic-based method, we actually see that as you're increasing more wind and solar onto your system, you actually get a drop in the capacity credit. So, and that's something that you might not see with the approximation-based methods. So for sure, system operators are looking into probabilistic methods, especially as wind and solar are increasing onto the system.
Mm-hmm. And limited duration storage as well. You would see a similar
for sure.
change.
Yeah. The thing is with storage specifically, with the approximated based methods, you're mostly looking at the discharging of the storage unit during the shortfall time period. So you could actually get a capacity credit of 100% sometimes for storage. However, with the probabilistic method, it's looking at your charging and discharging. So if you have bulk storage onto the system, and if charging a bunch of storage units is actually causing some stress during specific time periods, which are not the hours that you're considering in the approximation-based method, then that shows a more realistic capacity credit versus when you're only looking at a certain number of hours.
Right. Okay. So if we think about system like in India, where they have a target of 175 gigawatts of renewables by 2022, 450 by 2030, what's the risk of not taking into account capacity contributions of wind and solar?
Can you rephrase the question?
Sure. Given India's really ambitious renewable targets, why should they try to make sure they're taking into account capacity contributions of wind and solar?
Oh, okay. Yeah, because so wind and solar, these are variable, that's variable generation, and you have a lot of uncertainty with that. So capacity credit kind of helps you with determining how much your wind and solar can actually contribute to the system. So you would not really know how much a 100 megawatt wind farm would actually contribute unless you look into the capacity credit. And a 100 megawatt wind farm can give you different capacity credit depending on where you are or which region you're actually installing, because it depends on the load, depends on transmission, depends on a couple of things. So we can't really say that 400 gigawatt of wind and solar would give us 450 gigawatts of wind and solar would actually give us 450 gigawatts of wind and solar. It might actually give us way less. So we might need to find other ways to maintain the system, to maintain, making sure that the system is resource adequate. So that's why capacity credit calculation is important there.
And I would imagine, on the other hand, if you don't consider any firm capacity coming from wind and solar, you could end up with a very overbuilt system where you've built all this other generation that would end up not being used.
For sure, yeah. Yeah.
Well, Sarah, thank you very much. We actually got through all of our questions.
Awesome.
So if people want to learn more, they can go to the GitHub, but also reach out to you.
For sure, yeah. So okay. I have my email in the slides, and feel free to email me.
Okay, great. Well, thank you so much for all your excellent work on this. It's definitely a powerful tool, and one that's increasingly important in systems all over the world, and I think will be increasingly important in India. So I appreciate your time, and thank you to everyone who joined and asked questions, and please feel free to follow up with Sarah or with myself if you'd like more information.
Thank you.
Thanks, everyone. Bye.
Bye.